All right, so in today's session, we're pretty much going to do exactly what we did last week with the simple robot, or sorry, the sample robot, except we're going to now work with the iterative robot, and we're going to work with this model for at least a couple of sessions, and we might flip-flop between the iterative and command-based robot templates so you guys can see the differences between them. So let's go ahead and get started, and I'm going to explain the biggest difference between the iterative / command-based template and the sample robot. So again, we're going to make a new project, and then we're going to go down into the WPI section. We're going to do robot Java project, and we're going to call this summer sessions. Summer sessions iterative robot. And we're going to do this in the iterative template, and then eventually we're going to create a command-based template as well. So if we go ahead and open the project, there is going to be a robot.java class like there was in the other one, but this is filled with some different methods. And this kind of hints at the inherent difference between the sample robot and the iterative robot. So if you look here, it's still set up the same way where you have your robot class, and again, it extends an iterative robot rather than the sample robot. You still have your constructor, but where we go into the actual coding part, we have it set up in different ways. We have an autonomous init and then an autonomous periodic. And then if you scroll down, we have the same thing for the teleop mode. We have a teleop periodic and a test periodic. And what that means is that this code is run at the sample rate on the RoboRio. So all of these methods are pulled and called at 50 times a second, or approximately that speed or faster. And all of that is handled in the back end on the RoboRio, and which method it calls is determined by what your driver station says. So when you go onto the driver station and you click autonomous mode and then you hit enable, what happens is it runs autonomous init one time, and then it immediately starts running autonomous periodic in its own while loop. So that's something like if I were to go into the sample robot that we had before, you can see that in the teleop operated control, which was the essential teleop, we had to make our own while loop and have it do its own thing constantly. But in here, we don't need to do that because we know that it's going to run in its own loop. So a lot of the code is going to be the same. We're going to, just make basic. We're just going to have a 2-talon robot that's supposed to represent a drive base. I'm going to show you how to go ahead and add a sensor, and then I can show you how you pull sensors and stuff like that. So first things first, let's make our objects. So we're going to have 2 vectors, and we're going to call that left drive and right drive. We're going to import those, and in the robot init, we're going to set those to their respective, I spelled right wrong, and we're going to set those to their respective PWM channels like we did before. Let's go ahead and write just 1, and then right drive will be 10. So that's pretty much it, and then now we can start looking at autonomous init. So if you remember how a robot turns, since the motors are facing opposite directions, both of the vectors need to be outputting the same sign on a signal for the robot to turn. So if they both output a positive sign, then the robot will turn to one direction. If they both output a negative sign, then they'll turn in the other direction. So that being said, we're going to make an autonomous mode to rotate in a full circle and then stop. Or let's do half circle, turn 180 degrees and face the opposite direction. So some things that we're going to want to do is we're going to, want to make sure our vectors are set to 0 to start. So we can go ahead and just say left drive dot set 0 and rate drive dot set 0. So now let's go ahead and make our gyro, because obviously if we want to turn 180 degrees, we need some way to measure, what angle we're currently at and what heading we're currently at. So I mentioned this in our very first session when I talked about various control components, but the gyro that we use is a 2D gyro, so it can determine pitch and roll. And when we mount it horizontally on our robot platform, it tells us our heading from startup, and it gives us that in a PWM signal that is analog. So there is actually a gyro class in the WPI libs. So let's just call this my gyro. That's a bad name. Let's just call this robot heading, and we'll see if we can import that. Yep, it recognizes the WPI lib. And if you're ever curious about this stuff, you can right-click and go to Open Declaration on any class, and it'll actually open the physical class that it references. So if you're curious on what methods are available or how it specifically does something, so right here it just has some interface, and it has all these sample functions. So since this is an interface, it means that we're expected to use it on our own. I'm not exactly sure why they implemented it like this. I'm curious to see if they... so I'm not exactly sure if we're going to use it this way, but the way I do know that works is you can just make a analog input class. We're going to have to import that, and we'll just call that gyro in all lowercase. So again, this is just because we know that the gyro sends an analog signal on the PWM, we can just immediately do that. The one thing that this doesn't do that a gyro class would have done is limit your numbers. So if I were to read the gyro, it would tell me 4, and I would understand that to be 4 degrees, versus the analog input signal would be the raw analog signal. So we would have to, figure out a way to determine how many degrees that actually is. And I can actually show you, let's go ahead and do that, the gyro class that we used in the 2016 code from this past year. And let's try to figure out, it should be in drive. So this is their drive code. So we just used a regular gyro. And I guess we can just use that, and it works. I figured it wouldn't, but let's go ahead and do that then. So let's just call it a gyro. So again, down in robot init, we're gonna, I spelled it wrong. Robot init, we're gonna, instantiate it as its own object. So gyro equals, and we're gonna just say 1 for the port that it's in. What? That's what it is, I see. So yeah, instead of just calling gyro, we have to call analog gyro, so it, specifically knows that it's that. So with the advantage of doing it this way is we know that, again, we have some reference as to what the number returns to us. And that's a concept that you should kind of always keep in mind. Any signal that you're reading from, or any value that you're receiving from a sensor, is ultimately just a number in terms of code. So you're going to have to give that number meaning, whether that's here, whether that's a number being corresponding to the heading of the robot, and that a change of 10 in that physical signal is a change of 10 degrees in the robot, or that's an encoder where that 10 ticks is 10 inches or 10 feet or 10 millimeters. You just have to, give context to all of these signals. So now that we have our gyro and autonomous init, we're going to go ahead and 0 the gyro. And that's going to just make sure that even if I turned it on and spun it 3 times, it wouldn't try to reverse those 3 spins when trying to go to a certain angle. And this is a good practice to always initialize and zero your sensors that track various, robot heading or distance information. All of your encoders should always be zeroed frequently. So we're going to go ahead and zero this. And I believe it's calibrate that actually zeroes the gyro. So in autonomous periodic, I'm just going to go ahead and comment all of those out. If you guys want to know how to do that, you can just highlight a lot of stuff and hit Control / or Command / depending on what computer you're using, and it'll just put the comments on all of those. So we are going to spin to, let's say, the right. So that means that we're going to put positive signals on both of our vectors until we're at 180 degrees. So again, since autonomous periodic is run in its own while loop, we never want to put while loops in our code, because what that would do is it would go into its own while loop and halt the rest of the code. So if I were to just put a while loop here, for example, so let's just say while 1 is less than 2, which we know is always true, and I were just to say, like left drive dot set 1, and then, but down here, if I were to say right or left drive dot stop set 0, like we know that this would never happen. And it actually warns you it's unreachable because this is an infinite while loop. But even if this wasn't an infinite while loop and you know that it was going to stop at a certain time, what would happen is it would continue to do this every 50 milliseconds or whatever the rate that this whole function is run at, rather than continue the rest of the code. So just don't use while loops. For loops are also very, I recommend always avoiding for loops, just because they work in the same way where they'll block into their own function and continue to loop within themselves. But I've seen for loops used in autonomous code where if you know the speed of the processor, you can actually use for loops to time exactly how many iterations run and then continue to the next step and stuff like that. But I generally say to avoid that, just because you have better control with just using if statements. And if statements end up being like one of the best ways you can control it. So again, there are like blessings and curses with this the system that it runs and constantly. Sometimes if you want to have something happen for half a second, or like if you want a half-second delay before the robot shoots or something like that, it's kind of a pain where you have to use timers and then like account for the different scenarios. But at the end of the day, it's pretty useful to have this run constantly and not have to make sure that you can exit different loops to go to other parts of your code. So again, we're going to want to spin to the right, and we're going to assume, and this is a correct assumption by the way, that spinning to the right is an increase in the gyro angle. So it'll if you start at 0 and you turned it a quarter revolution to the right, your gyro would read approximately 90 degrees. And something of note with gyros is they do drift. So the longer they're on and the hotter they are rather, the more there is drift. So that's another reason we calibrate it right before we want to run it. So let's go ahead and do that. So we're gonna just have an if statement, because that'll make sure that something is being checked every time. And let's go ahead and say gyro.get angle is less than 180. And what we're going to want to do is we're going to say left drive dot set 1.0. Let's go half speed just to make sure that we're going to get there and not overshoot. That's something that is critical to know. If you're trying to do something, it's always better to start slow and speed it up, just so you know what happens. One of the first things that we do when we power on a fully functioning robot and start to download code is you give it a really small signal and make sure all your vectors are moving in the correct direction. You don't want vectors to fight against each other, because that could destroy components and stuff like that. So starting slow is always good. So so we're going to make, while the gyro is going to read an angle less than 180 degrees, we're going to turn, which is what this code does, and then we're going to say else we want it to stop. So left drive dot set 0 and right drive dot set. Cool. So if we were to run this code, it would, I was trying to save. But if we were, going to run this code, it would go into autonomous init. It would start all of the motors at 0. It would calibrate the gyro, and then it would, start turning until it hit 180 degrees, and then it would immediately stop. So there's not going to be any speed up. There's not going to be any slowdown. It's just going to, go until it hits the angle, and then it's going to stop. And this in the robotics world and in the real world. It's called bang bang controller. What that basically means is run until I hit something and then stop. And that something is going to be the set point. So I want it to, so in this case, I want to turn 180 degrees, so I'm going to, turn, I'm going to send my motors a signal to turn until I hit 180 degrees, and then I'm going to tell them to stop. In a shooter, this could be, I'm going to tell my wheels to start turning until they're at a certain speed, and then I'm going to tell them to stop. Or in driving, I'm going to drive forward until my encoders tell me I'm 10 feet from where I started, and then I'm going to stop. So this has very good benefits, especially the flywheel shooter. But when you have something like a drivetrain that you're trying to control, it's probably one of the worst ways you can do it. Simply because, if I'm going at a certain speed and then I immediately hit the brakes, like imagine you're in a car, you're going at 20 miles an hour, and you hit the brakes. You don't stop moving for another, 10, 15, 20 feet. So the same way, your robot's not going to stop as soon as you want it to stop. So in our specific case, our robot would probably turn anywhere between 190 and 200 degrees when we wanted it to turn at 180. So there's a couple ways to handle that. You could always just change this 180 to, let's say, like 175, 170, maybe even 160, depending on how fast you're turning. But that'll only be a specific solution for the exact speed that you're running. And let's say I put like a 30-pound weight on our robot, that would change it as well, because it would have a larger mass, so it has more inertia, and it's like rotating. So again, that's a very poor solution, given that robots change, the weight changes, speed might change later on when you want to go a little bit faster. So I'm going to go ahead and teach you guys how to do P-level control, and this is like this is the most basic step to doing PID control. And it involves two things, right? You need something to measure, in this case a gyro, and you need a set point. So our set point is 180 degrees. We obviously know that. So let's go ahead and start doing that, and we're going to explicitly declare some stuff. So we're going to make a double, and we're just going to call it error. Error is the difference between your measured value, in this case your gyro angle, and your set point. Think about this as like the time remaining, or how far do I have to go. And we're going to base all our math on this value, because when our error is high, that means we're far away, we haven't even started moving. When our error is low, we can we're getting closer and closer to our set point. And it makes our math a lot easier. But one of the biggest things we need to, think about is BIBO, and this is a design philosophy with any type of controller. It means bounded input, bounded output. So we know that our speed controllers can only output a signal between -1 and 1 rather. But we know that our input can be any number from 0 to 360. So both of those numbers are bounded, and that means that we can create a system that is controlled and does exactly what we want. If you have something that's unbounded, i.e. you're trying to control something to go from 0 feet to infinity feet, then you're going to have a really tough time controlling it to do motion in that range. But within the realm of FRC, like any subsystem that we create, whether it's a drivetrain or an elevator or a flywheel shooter, all of our motion and stuff like that is bounded. So we know that we can create some system, whether it's just a proportional or it's a full PID loop. We can control that and have it have smooth motion. So yeah, we have our error, and I'm gonna just go ahead and explicitly call our make a variable called setPoint, just so it's a lot clearer for someone reading over this code. And let's go ahead and make just current. Error current is a bad measure. Let's just call this current angle. Okay, and we're gonna have to set those to 0 in here, or rather we don't, since they're primitive types, my bad. So in here, in autonomous init, we're gonna go ahead and say we want our set point to be 180. And we know that we know that just because that's given by the constraint that I said. We want our robot to turn in a half circle. And we can actually go ahead and get our current angle, and that's going to be gyro dot get angle. And then because we have those two values, we can go ahead and calculate our error. Our set point minus our current angle. So this is the only line that you're going to need, or I guess these two are the only lines you're going to need to use anywhere else. And these two, we can just go ahead and copy those and paste those into autonomous periodic. So what's going to happen is, as soon as the loop starts, it's going to calculate the current angle of the gyro, and then it's going to recalculate its error. So now what we're going to do is, instead of gyro.getAngle is less than 180, we're going to say if error is greater than 0, then what we're going to want to do is we're going to turn at the speed. Else, that means it's less than or equal to 0, which means we either reached or overshot our set point. Stop. So if we don't change this code right here, it's still essentially a bang-bang controller. Like we didn't do anything with the motion profiling, in the sense that we didn't change how the output to our speed controllers changed at all. We're just calculating that value differently by calling it an error rather than doing it based on the current angle. And this is where the PID terminology starts to come in. So PID stands for proportional integral and derivative control. Right now, we're just going to implement a proportional loop, and it's exactly what it sounds. We have some proportional term where the higher the error is, the higher you should move your motor, and the lower the error is, the lower you should move their motor. So the easiest way to implement that is by multiplication. We can just say that output equals some constant, and we're going to call this Kp for the proportional constant, times error. So again, if we look at this statement, if Kp is really, just say Kp is 1, when error is low, maybe like 3, our output's going to be 3. When error is high, like 180, then output's going to be high as 180. So given this in mind, how do we find Kp? Well, let's start to think about it. If I want my robot to stop at exactly 180 degrees, we can think about what number we would want it. What's the highest number of degrees we want it to spin at full speed? So if it spins at full speed for maybe 90 degrees and then starts slowing down, it can probably reach 180 degrees fine. So for that, we want this to be 1 over 90, because that means when this is 1 over 90 and then error is 90, the output will be 1. And then any value less than that for error, or sorry, higher than that for error, will do, obviously like less and less and less. Is that right? No, I think that's wrong. It should be 90 over 1. Air's 90, output 1. Yeah, I want KP to be 1 over 90, basically. So that when air is, so when I'm at 90 degrees, I want the output to be 1. Yeah. So again, so we're going to follow this same thing here, and we're just going to implement that in the set. So we'll just call this, 1 over 90 times error. And what's going to happen is as it gets closer and closer to the output, it's going to slow down because error is going to start shrinking as it gets closer to 180, and that means that it's going to set progressively lower and lower values until it turns 190, until it turns your full range of 180 degrees. So that's pretty much how you do proportional tuning. And if we were to look at our drive code from last year, let's go ahead and open one of our autonomous modes, mixed turn. You can see that right here in running, I guess we didn't implement the PID for the drivetrain because we didn't actually code it, but I could show you code that proportional gains for gyros is pretty much all you need. It ends up being really good because there's a lot of friction with the drivetrain and turning. There is like decent amount of scrub. So any amount of like control where you're trying to slow down as you reach your target ends up being plenty to stop on the dime. And there are other ways to do it where you can, have like various set points in a trajectory, and that's how, teams like 254 do it, and they can, drive in crazy splines and do different things. It's just if you want to implement all those features, you can. If not, you don't have to. But this is a very simple way to do that. So yeah, that's pretty much how you do proportional tuning, and this was just to get you a decent idea on how to work with the periodic and iterative models. That's pretty much all I had planned for today. For next, or not next week, sorry. In 2 weeks, at some time between August 6th and August, I guess 12th would be that Friday. We'll have our next session, and we're gonna go ahead and make a subsystem. We can just call it an intake, and then we can add our pistons and motors and all of that good stuff, and then we can start implementing it into the robot code and control different buttons with that. But yeah, that's pretty much all I had planned for today. Thank you guys for coming, and I guess I'll see you next time.